Hi friends, welcome back to another video in the series The Ray Tracer Challenge by James Buck, where I implement a ray tracer based on this book, The Ray Tracer Challenge, in Rust, a language which I'm learning while doing the series and going along with this ray tracer. The last time we implemented shadows. Let's have a quick look what we did there. I can render the executable here real quick. We are using the same executable actually than in the session before. Oh no, that was wrong. Let me render this in release mode to have a lot quicker rendering there, because the compiler does more optimization. So let me open the output and put it into view. This is what we created the last time. We implemented already before all this, the possibility to create a scene, the possibility to create a camera which looks at the scene, a positioned light, lighting models, Phong lighting model to be precise. And in the last session we implemented those shadow casting here, which you can see here now. We even created an animation the last time based on all of those shadow information. Let me quickly show you this again. There it is, and yes, and let me make it a little bit smaller. There we are. As you can see, we are rotating the light around the scene while the spheres are moving, which creates this nice little moving effect. Okay, that is what we did last time. This time we want to go ahead and implement our next body object, our next shape. Until now we only have spheres. We have implemented the sphere object, which in turn is an intersectable. It implements our intersectable trait here, which provides all of those nifty methods like intersect, normal add, material, and so on. Now we want to implement the next body type, and this will be a plane. So essentially we will be creating what we more or less cheated us together here and used for the walls and the floor, which essentially is nothing else here than a completely squashed and flattened sphere, because we do not have anything else. But now we want to implement planes, which are simply some essentially two-dimensional objects in three-dimensional space along a certain rotated or created axes, two axes to be precise, and are just expanding in the infinity there. So essentially what we want for a floor or a wall or anything else which we might lie into 3D space. Before we are going along and actually implementing those new body types, we want to refactor the old ones a little bit, only a little bit. Because what we can see here is, in the intersect object, we are first transforming our incoming ray into our object space to ensure that the ray can be calculated always based on a sphere which is at the coordinate center 0, 0, 0. And we want this for any other object that we are going to implement, or any other body as well. Same goes for the normal. We are first transforming the incoming point, which we are calculating the normal vector for, into our object point, then calculating the normal in object space, and then transforming it back into world space. This is always possible due to the usage of our transformation matrix, which every body object needs to implement. We are doing it here inside the calculation itself, and as we will need this for all our calculations, all our bodies in the future, we want to extract it. And therefore we need to take a look at our intersectable trait, because our intersectable trait could be a little bit different. What we are going to do now is we only enforce the implementers of this trait to implement the intersection and normal calculation based on their object space. and do all the transformation needed around that within this trait so that we don't need to implement it over and over and over again. So yeah, let's start with this, I guess. So what we need first is a corresponding function. So let's introduce one. Fn, let's call it intersect in object space. And it takes, of course, a self as well as object space. Oh, there's a J missing. Object space array, which is array, of course. And what we are returning here is, what we are normally returning is an intersection. But we might get a problem here. Let's see how this intersections struct is actually structured. It takes a vector of intersections, and intersections take the t, so the position along the array where the intersection happened, the array itself, and the body object. And there we have essentially two problems, I guess. First of all, we cannot return this array. We could only, if we are changing this, return this object space array. But in what the intersect method later on needs to return, we need the global array, the real array. We could, of course, replace that, but I guess we will simply return a vector here, I guess, of a tuple which consists of a floating point value and a body object. We need to return the body as well, because only the real implementation can decide which kind of body we are using here. So only a sphere, for example, could know that we need to put a body of the type sphere in there. So it's not, or it's needed to specify this in the implementation. So now we have this method here. Oh, we need to import f. Yeah, let's import f here. After we have this method, let's implement a default for our intersect method here. And maybe let's reorder things a little bit so that the defaults are at the end. So what we are going to do now here is we are taking a, where is it? There, intersect. We are taking this transformation here from this sphere method itself and putting it in here as a default implementation. So now we have this transformation. The only problem is inside of this trait we cannot access the transform property of the struct because we don't even know if the struct supports it. So we are just introducing another function here, the same we did with material, to get this transformation, and we call it transform self, and it returns, of course, a matrix of 4 columns and 4 rows. So let's import this. So now we can use this here, but we are still not returning this intersections stuff. However, that shouldn't be a big problem. We can simply tell the system to have this intersections and to create new intersections here. And now we need to take our result here. No, we first of all need to get our t's. So we are calling self dot intersect in object space with the object space array, and now we are getting back, as you can see here, our vector of globals tuples. And so now we can do a ts into iter and map it, and we are taking out there, we are taking, I guess, let's destructure this directly, a t and a body. We need, of course, to collect this later on. And now how do we need to, we have this t's and we want to, that's wrong there, needs to be an iter, and then we are mapping it, and we want to map it to intersection new, and we are simply using it here. We are putting our original ray in, and we are taking the body object. And this should actually work then, but it does not. Why does it not? Let's see. Maybe because we need to dereference this body here. Mismatch type F64 found. Yeah, we are getting references to. Oh, I see. If I make this into an iter, it should be all right, I guess. Mismatch types. Yeah, because there's a semicolon which shouldn't be there. So what we're actually now doing here, we are getting from our intersect in object space method, we are getting this tuple of F64s and body objects. And we are then creating a new intersections set here where we put in an array, which is created by this mapping here, which uses those structs here, those tuples here, to create for each of them a new intersection with a corresponding t, the ray, and the given body. And then, because iterators in Rust are lazy, we are collecting this. I'm not even 100% sure that we need this. Let's check. Yeah, we need it. Okay, so let's collect this in order to make a vector again from this iterator, which we can then put into this intersections thing. What we have done now essentially is we have refactored this in a way where we can now do this, of course, below here. We need to change this in the body base implementation, because we now need to send it to the correct implementation here, which is now, of course, intersect in object space. Not all trait items are implemented. Yeah, transform is not implemented. We should therefore implement this as well in order to pass through all calls to the transform function to get a transformation matrix just to the corresponding function on the object itself. Now this implementation is finished. However, sphere is not okay yet because we haven't adapted this function here. So I guess let's do that as well. We have now here this object space ray which we get there. However, now we need to change the return values, of course. In case we missed the object, we are simply returning an empty vector. And in case we have a match here, we are returning a vector of tuples, which always have the body as well as the t value in there, but not the ray anymore. And I guess there we go. Let's reformat this. Yeah, and of course we need to implement the transform method as well. So let's do this here as well, which returns, of course, a matrix of size 4. So now our trait should be able to access everything, and as we can see, everything is not red again. And what you can see here now is why we needed to return this body from the implementation of the specific body here, because only the compiler can only know in this situation that it should create a body which is essentially, here let me show you, is essentially an enumeration which we are using for dynamic or a kind of a static dispatching here. It can only know here which of the implementations it should choose, because only now it knows that it is actually a sphere. So we need to return it. We want this generalized body enumeration here, but of a specific type, of the type sphere. And that is why we needed to return it here. So let's run our tests, I guess, and let's check. Okay, I have some imported stuff there. But the tests are all running, which is nice. So we didn't really make something break entirely, but we have somehow now imported create intersections in sphere, which we don't need anymore. Yeah, because we are not returning intersections anymore, but we are returning those tuples now. And now the tests are all running and everything is fine. So this works out. What we still need to change here is now our normal add function, because we have only integrated this object space mapping into our intersect function. But as we can see here and saw before, we are doing all this transformation here for our normal add function as well. So yeah, let's start transforming it as well, I guess, by copying it down here for our new default implementation and creating a normal add in object space method here, which in this case can easily return a tuple. So we have now this, and we need to fill this one with live. So we just take out for now all of this and put it in here or into our default implementation. We can use our transformation, which we now extracted there before. And we have this object point here. Exactly. Now this is the point which should be done by our specific body implementation. So here we will do a normal add in object space, and we will put the object point, or let's rename this to object space point, in there. And then we are again transforming back the result into our world space again. So what we need to do now here is, of course, we need to adapt this here and say normal add in object space, which should just work out fine. And we do it here as well and say normal add in object space, and let's rename this here to object space point. Not strictly necessary, but I like it to be the same as with the declaration. So now we have this there, so let's adapt it in our sphere, and let's implement here now normal add in object space, and we are getting, let's remove this, our object space point. And I guess now we can remove this. We can remove all this because it is now done by the default implementation, and we have our object space point here. We only need to return this now and we should be golden. Let's see. So, oh no, we need of course to normalize this whole vector here. So let's put the parentheses there. So essentially this should be everything we need to do. Let's run the tests and let's see. And yeah, this one ran nicely and fine. This is okay. So let's take a look what we need to do to implement a plane. First of all, of course, we need to create a new file for it. So let's call it plane.rs. And let's integrate it into our, where's our lib.rs? There's our lib.rs. Maybe we should put it directly below the sphere, which is here. So pub mod plane. So now that it is imported, we can start defining it. Now let's see if there is something that any body object needs. I already know, of course, what this is. The sphere, in our case here, no, not body, sphere, I opened the wrong file. The sphere, of course, has two properties which we'll need, the transform and the material. And essentially we will need exactly the same for our plane. So we can more or less copy this or implement it again. So let's create our pub struct plane, which will have a material, which is a material. and, oh no, comma there, and it has a transform, which is a matrix 4. And we of course need to import this, and we need to derive certain properties here. We need to derive copy, clone, debug, and partial equality, because we need all those for later on for tests and stuff like that. So now after we have this, let's check the sphere again. We have this default for a sphere, which is quite nice, and I would like to have it for our plane as well. And we can, I guess, transfer over those new and with material and with transform functions as well. Let's just copy them. Maybe we can think about later on if there is a way to change this into something that we can reuse as well, but until now I don't have a real good idea of that. So for now, let's implement the default trait for the plane, which provides us with a identity transform and a default material. And then let's implement the new here as well, which takes material and transform. And of course it now can actually change this to have easier copying in the future, which takes a material and a transform. And we have this principle here where we can create it with a material and with a transform, which is quite nice. So now we have the basics of our plane, but the real interesting stuff now happens with this implementation of intersectable. So let's implement intersectable for plane. And of course we need to import this. And now we need to implement all the missing members, which for one is the material function, which is easy to implement. Material there, which is the transform function, which is quite easy to implement as well. Self transform, there we go. And now we need to implement intersection and normal. Let's first implement the normal, because the normal of a plane is actually quite easy. We need to think about certain things. We have defined that, for example, our sphere is always in the center of the coordinate system, because we are always describing our objects to their own object space. We have said it is always centered at 0, 0, 0, and it has always a radius of 1, which makes things for our calculations a lot easier. For our plane now, we will assume that it is a plane. So our, it's essentially a perfectly flat surface that extends into two axes infinitely. So what we are going to do is we are using the XZ plane here. So we are lying it essentially in the X direction is one of the axes, and the Z direction is another one. So we essentially have this, you could say floor plane, the one that is at the 0, 0 position and extends into the X infinitely and into the Z infinitely. So this is what we are actually going to implement. And as it is perfectly flat and just lying on this coordinate space, you can simply determine that its normal vector, if it's an XZ plane, needs to be, the normal vector always needs to be perpendicular to the other two axes there. So it is obviously the Y plane. So in every situation that we want the normal of a plane here, of our plane in our world, in our object space, we are simply returning the vector, which is 0, 0, 1.0, 0, 0. We don't even need to normalize it here because it is already normalized. So this will be the normal vector for each position which we are calculating on this plane. And I guess it's quite easy to understand why this is the case. So now we need to actually implement intersection in order to use our plane. So let's think about intersection for a second. There can actually be 4 different cases within this intersection and array. First, our array is parallel to our plane. So here's our plane and here goes our ray. It is so parallel to our plane and will therefore never intersect with it. The second one is that the ray is coplanar with the plane, which means that the starting point of our ray, the origin point, lies on the plane itself, and the ray's direction is in one of the directions of the plane, so that essentially every point on this plane will be a hit. This can actually only happen if you are looking, if it's directly the edge of the plane you are looking at. And yeah, that is kind of hard to calculate, and it would be a real problem because we cannot express unlimited hits there in our language, and our memory of the computer is not infinite, so this would not work, at least not easily. We could of course do something like this, and yeah, but we don't need to actually, because our plane is assumed to be infinitesimal thin. So we are simply ignoring that fact and looking at it the same way as the array would have missed the plane, because it will not make any difference. The next two are the more interesting, which is either the ray hits the plane from above or the ray hits the plane from below. And those four cases exist. So how can we determine case 1 and 2, parallelism with our plane? When is this vector or this ray going to be parallel to our plane? It's quite easily answered. If the y component of our direction vector does not have any change in the y, it needs to be parallel to our xz somewhere. Either it lies directly on it, which is our case 2, or it is simply parallel to our xz. So I guess this will be our first case. If our object space ray is less than or equal, and you might now ask, why is he doing a less than or equal there when he just said that it needs to be 0, and there is this floating point thingy again that we had all the time. So I'm taking the absolute value here from our object space ray position y, and then I'm checking it against our epsilon value. And if it's smaller than this epsilon, we are assuming that it is actually a 0 and therefore parallel to our plane. But don't I have position? No, not position, direction, of course. Direction y, exactly. And in this case, we are simply returning an empty vec again, as we don't have any collisions with the, let me remove the return here, we don't have any collisions there. Yeah, and I think I want a clear return there because I want to stop the execution there. And now I need to take a look at case 3 and 4. So hitting from below, above and hitting from below. And again, for calculating now our t value for our intersection, we only need to take a look at the y value, because both other values, the x and the z, aren't really interesting for us. Because the only thing that we really need is the slope of our vector. So if we have this plane here and we have our vector here, and it is, for example, like this, then it would hit the plane somewhere here, and we need this slope actually, how fast it is going to hit this thing. So how many what kind of time or length of this ray is needed to in the end hit the plane, because we are definitely sure it will hit somewhere, but we are not sure if it is somewhere near infinity or if it's more or less directly before us. And actually we can calculate this by using the following information. Our t equals minus our object space ray origin y divided by our object space ray direction y. This will create the correct position where our ray hits the plane. So I guess we are now returning this here as well. T and body from self. However, we of course need to import body. However, this will fail because we don't have taught the body yet what a plane type is. So this is actually what we need to do next. Let's open up body and create a new body type here, which is a plane, and it gets a plane there. And we of course need to import the plane. Now we have this, and now we need to implement a from for body is correct, a from plane for body, so that we can actually create a body from a plane. There we go, and we are putting everything together here. And now we need to add, and the compiler is already complaining here because now we have more than one type to differentiate here. We need to essentially copy this here and adapt it for being a plane. So let's replace everything sphere here with plane, and let's do the same thing for the lowercase version of it. And let's do the same thing here. And let's do the same thing here as well. And here again, one last time. Now we can map all those calls correctly to the corresponding type here, and the compiler knows where to map what. We are actually ready to render our first plane now, at least I hope. Okay, this still does not work. Why does this not work? It should work. Okay, so this does not really work. Why does it not work? Expected type vec. Oh yeah, of course, because we need to return a vector here. It actually told us what is wrong here. We need to always return a vector of intersections here, even though we only have one here. But now this should actually compile. So let's try this out by copying our last chapter here, calling it chapter 9 now, and let's remove the floor and the walls. At least let's remove, I guess, let's name this floor material. Let's remove the walls here. Middle material, left material, right wall sphere there. This can be removed, and now we are using this floor material here, and we are not creating a floor sphere anymore, but we are creating a real floor here, which is now a plane, and we of course need to import it now. And we don't need to scale it anymore because it already sits at the 0, 0, 0 position. However, this might cut all our spheres in half. We will see. Maybe we will need to move it later on, but let's change this. So with material, there we go. So now we have our floor here, and now we can remove those walls here and simply put in our floor there, our new type. So now let's try and render this. Cargo run bin chapter 09 release. Okay, we get a warning here. Prefix with an underscore because we did not. That's actually a proper warning. Let's fix this quickly because we did not use the given point within our our normal add in object space of the plane. Rust tells us to please prefix it if you don't intend to use it, just to show that it is not used and not that this was unintentional. So yeah, let's render again, and as you can see, the warning is gone. It wouldn't have affected the render, but I wanted to get rid of the warning. So now let's open the output and let's see. And as we can see, we have a flaw still, even though we now have a plane, but it would be nicer to better see this flaw. So maybe we should just move the camera down a little bit, which can easily be done by us. So let's close chapter 7 and let's check where we define our camera. It needs to be somewhere here. There we are. Look at from position, and our position actually is quite high. So maybe we are now looking at it from 1.5 and not 3.5, and let's see what happens then, because then we should be able to see the plane going into the infinity, maybe, or we need to get lower still. Let's see. Yeah, there you can now see that this plane actually goes there into infinity, and it isn't here above, but it's only down here, and it's going into infinity there. Actually, I like this very much, and now we have the capability to implement real planes. We could, of course, create new walls of this or with these planes now, but yeah, I think we will end this here. As we've now successfully implemented a new body type sphere, our first new body type, and there will be more. We will be implementing cubes, and we will be implementing, I guess, polygon models at some point. I'm not sure if the book does, but I will do it definitely at some point. And yeah, I'm very happy and glad that you joined me again in this next installment of the Ray Tracer series. Please comment the videos if you have any questions or suggestions. Please give the video a thumbs up if you liked it, because that really makes a difference for me. And yeah, subscribe to this channel to be informed once the next episode is out, or one of my other videos and other episodes is out. The next time we will actually take a look at implementing patterns. This might be then, there might be multiple sessions until we have implemented patterns, but we will see how long this takes us, because it is a little bit complex, but it can be done, and it is an amazing effect afterwards. So thank you for joining me again, and I hope to see you the next time. Bye!